Alright, so let's go ahead and talk about half-life. When you think of those words, what do you think of? First, well, let's break it down. What does half mean? That is kind of a Mr. Obvious moment, right? Half is 1/2. Half is 50%. Half, if earlier I drew a circle and it was the world's worst circle, so I'm a little nervous. That's not that bad. Half is half. Right? That seems like an easy enough part of the word. Life, we'll just say life is exist. Or to be. Being. Being what it is. Okay? So when we think in these terms, this word is very simple. And I don't want it to get any more complicated than that for us. But we need to put it in terms of radioactivity. So yesterday we talked about radioactivity, and we'll kind of flip back to that page where we said that in radioactive decay is decomposition. So the unstable atom likes to throw things until they reach stability. Okay? And all that they have are the protons, neutrons, electrons. So when they throw things, they change. They become something else. So keeping that in mind, let's go back and think about this half-life business. Half-life is the time. So time is that's a part that isn't in the word itself, but the time for 1/2 of a material, we'll just call it a material for right now, to decay. And we want to remember that we're talking about radioactivity here. Right. So on the flip side of that, you have half of what you started with left. So we might write that down to be very, very clear. After 1 half-life, make that look like a 1, not an L. After 1 half-life, 1/2 of the original sample is there. Okay. Give me a thumbs up if that makes sense, and a thumbs down if you're like, nope, still talking in a different language. Okay, so that makes sense. All right, let's just break it down with some fractions. Okay, fractions are going to be something that we need to talk about as we go through this part. Okay, so I'm going to use a Postit Note, and if you guys want to flick the light out, you can, so you can see that a little bit better. It's kind of your choice on that. All right, so if I have one whole Postit Note here, right, this is going to be my whole sample of Posty McElement Posty. Okay, and after 1 half-life, so after the time it takes for me to finish all this talking, okay, I'm going to have half of my Post-it note left. Now, question. Matter cannot be created nor destroyed. So what happens to the other half? Where did it go? What happens to this half? Go back to that definition. It decayed. It became something else. So this half has effectively thrown all of its parts to become something else. So let's go ahead and note that. We have after 1 half-life, I have 1 half left. Reasonably understandable, right? So what happens to this? If it's left, 1 half of it's left, what happens? Does it continue to decay, or does it just sit there happily unstable? Nope. That's the thing about atoms. They never sit there happily unstable. They always try to get to stability. So it continues to decay. So after 2 half-lives, what am I going to have? A quarter. Right, exactly. So that's perfect. Let's go ahead and note that in our after 2 half-lives. I'm going to have 1/4 left. So we'll go ahead and make a list. Okay? 1 half-life. I'm going to have 1 half left. Now this might seem like a Mr. Obvious moment, but let's make sure that we're taking it in, because as we know, all these things build on top of each other, and so we have to use them together. So after 2 half-lives, we determined that we would have a quarter left. Is it going to sit there happily unstable? No, they will not sit there happily unstable. That whole term doesn't even make sense. Happily and unstable, that doesn't go together. So what's going to happen after 1/3 of the half-life? I'm going to have 1/8 left. So let's write that down. I think you get the idea. So let's kind of continue down the list. Make this where you can see it better. What about after 4 half-lives? 1/16, right? And 5 half-lives? 1/32. And we could continue and go. 1/64. Oh, what's 7? 1/128, right? Okay. So whatever my original sample is, if I know that there have been 4 half-lives, I know that I have a 1/16 left. If I know that there have been 6 half-lives, I know that there will be 1/64 left. Okay. So that's kind of a simple breakdown of what we're looking at with half-life. Now, why on earth would we need to use this? Why on earth would we need to think about this? Have you guys ever heard of carbon-14 dating? So here's a why. Why? Why do I need to know this? Carbon-14 dating. Do you ever hear about like how old a fossil bone is, or like, hey, this petrified rock is from 1 million years ago, or from history, and wonder how do they know that? Well, this is how, because carbon-14 will decay. And there's a certain amount of carbon-14 in every living thing. So, I mean, it's not like the kind of radioactive stuff that's going to cause you to be ill, but it is the kind of radioactive stuff that we can put a marker on. We can look at it and see how much there should be. Because you should have a certain amount of carbon-14 given your mass and your size and what kind of species, if you're a plant or an animal or what you might be. So the half-life 1 half-life of carbon-14 equals 5,700 years. Okay. So what they do is they say, well, if I know how much there should be in this dinosaur or in this tree, and I know that there's only 1/32 of it left, then I know that it has gone through 5 half-lives, and I can tell you how old it is by multiplying the number of half-lives by the number of years. So half-life is important for that reason. It's also important for some other nuclear kinds of chemistry. Okay. All right. So hopefully you're starting to wonder, well, if these things are radioactive and they're unstable, we talked about that yesterday, they're unstable, they're trying to reach stability, why don't they just throw all of their little things at one time and become stable? Why does it take an entire half-life? So why does it take 5,700 years for carbon for half of the carbon-14 to decay? Well, hopefully, in the simulation that we're going to do next, it will make a lot more sense. As you think about the simulats we're going to use are going to be atoms of this carbon or atoms of any other thing that might be radioactive.
Okay, so today we're going to go through the Atoms Lesson 8 HalfLife Lab experience. You can watch this video at your own leisure. And then today, the HalfLife Lab, we're going to complete this lab today. This link right here is to the actual PDF from the science store. This link right here, click here for the file you need, takes you to the Google Doc that will allow you to fill in your data way more easily. Okay. So when I click here, I always like to right click, open in a new tab. And then this is what we open up to. You will want to hit File, Make a Copy of. And I like it when you make the title have your name. So you want to put your name in there, and that way I know just by glancing at it while I'm grading it what student it goes with. Okay, so radioactivity and half-life. The radioactive half-life for a given radioisotope is the time for half of the radioactive nuclei in any sample to undergo radioactive decay. So we've already talked about decay, the alpha, the beta, the gamma. But if half of the sample is gone, then it's undergone a half-life. That's the definition of half-life. After 2 half-lives, there will be 1/4 of the original sample. And after 3 half-lives, 1/8 of the original sample, and so forth. So our procedure is right here. Shake and toss a given number of simulats. I'll show you what that is here in a second. Remove and count those that land white side up. Record the number of white side up pieces in the table below. Those are going to represent the ones that have decayed, that have changed from whatever our original sample is into a different nuclei. Replace the ones that are red side up and repeat steps 1 and 2. Until there are no more pieces to flip. So we're going to record our data right here. Here's the number of tosses. We may need to add some more. The number of simulats removed, so the white side up. You notice right here it says no data. As we add data to our data table, this graph will fill in automatically for us. And then there are some questions here that we will look at the end. So let's look at our simulats. In this case, the simulats are these white and red little circles. You notice that right now all of them are red side up. So we are going to shake them. And now we're going to take all of the white side up ones out. So 1, 2, it's better to count them as you go. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Here's one back here, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Oh, here's one over here, 32, 33, 34, 5. There's one back here, 36, 37, 38. I don't think that one counts because I just turned it over. Okay, so we have 38 that we just removed. We're going to go back to our data table and we're going to type in 38. Notice our graph here automatically filled in. We're going to flip again. All right, so that one flipped over while I was touching it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So I took out 40 that time. All right. And then let's try again. Okay. Now 1, 2, that one flipped over on each side. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, that time we took out 16. Okay, let's do again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, that time we took out 23. We'll come back and we'll put in our data 23 Simulats. We're going to try again. Last one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, let's continue to flip and see what we got. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 that time. Okay, we'll go back and try again until we get no more Simulat. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9,
10, 11. Okay. We'll do card count. 1, 2, 3, 4, 5, 6. That time. Notice it's not the same number every time, because that's how probability works. We're not going to get exactly a certain number, but let's try this one more time. It won't be one more time, but we're going to try again. So that time we got 4. 1, 2, 3, 4. And we'll try again. Last time we got 4 or 5. Yeah. 1, 2, 3, 4, 5. We're going to continue again until we get, so there's no more simulats. Oh, we only did one that time. Okay. I'm going to go ahead and insert a couple rows so that we can continue our data. And we'll go back to our camera and flip again. That time we got 4. And then flip again. And we got 4. No, 5. Yeah, 5. A couple more rows. Okay, we'll go back to the camera and look at it again. We only got 2 that time. I feel like this might take a little bit. And we'll try again. No, we got 2. Okay, so let's look again. I'm going to spread these guys out a little bit. I don't know if I'm helping them or not. It's probably falsifying data in some way, shape, or form. All right, so let's try flipping them or shaking them. Okay, that time we got 1, 2, 3, 4, 5, 6. Let's try again. We're going to shake them. We got 2. And if we look back at our camera, we have 1, 2, 3, 4, 5 simulats left. Let's try again. Now we got 1. Turn over white. And okay. Let's try one more time. And look at our camera. We got 1. Probably far enough to look at our data. So let's go ahead and digest the data that we have. Okay, so the first couple times we had 40, and then the third time you can kind of begin to see a trend. And then there's the outliers, of course.
Okay, so we're going to continue this experience and kind of digest the numbers that we looked at with the simulats. First thing, I'm going to move this graph over just a little bit so we can see this graph kind of tells us some information, but let's really think about what we're looking at here. So I'm going to analyze the data a little bit. Find out what is our total number of simulats. So we're going to equals sum, enter a formula here that will give us the total of our simulats. We have 197 total simulats. All right, well, what is half of them? If we want to find out what half-life is, we need to know what half of the simulats are. So we're going to say, we're going to label our data half. Okay. All right, so now we're trying to figure out what is half of our simulats. So we're going to say equals our total simulats divided by 2, and that will give us half. So 98.5 is half of the simulats that we have. All right. How many tosses did it take to get to 98.5? So if we look at the first two tosses combined, were 78. All right, well, that's not half. 78 plus 16 gives us 94. That's almost half. But if we did a whole nother toss, that wouldn't quite be half. So 94, I need 4.5 more. So when I look here, that doesn't quite equate to a whole. So we're going to just kind of look at it for almosts and say that 3 tosses is about a half-life. And so first half-life, all right, kind of go here, equals total up that first half-life. .94, so about. So that would be these here. We'll go ahead and color them so that we have an idea. The second half-life, labeling is important. Second half-life. The next 3 tosses. And so that, let's go ahead and label that a color. These 3 tosses. And what is that total? 53. Now notice here, 3 tosses was about half. The next 3 tosses was about half again. All right. So hopefully we can start to put this together, and let's look at the next 3 tosses, and we'll make this, color might be hard to see through. Let's make it yellow. That equals the sum of all right, so we can see in the next 3 tosses, we have about half of what was left. So we can tell that the half-life for simulats is 3 tosses. That 3 tosses might take 3 years, it might be 3 days, it might be 3 minutes, it might be some other expansive time. But every 3 tosses, we get about half of our simulats to have decayed. Notice that they just turned into something else. When in our simulation, the simulats turned white, they were something else. They had radioactively decayed, they had emitted an alpha or a beta particle to change into something else. They didn't disappear, they weren't consumed, they just became something else. And what was left was our red simulats. So we can kind of see the purpose of this activity is to understand that even though in each toss we didn't have the same number of simulats turn over, now we can see the purpose of what we were doing to see how many tosses it would take to find how we would discover the half-life of the simulats or of an element. Okay, so if we come down here and we look at the question, if the half-life of carbon-14 is 5,700 years, what fraction of 14 still remains in charcoal burned in a primitive man's campfire approximately 28,000 years ago? We're going to go back to those notes that we took a little bit earlier, and we're going to say 28,000 divided by 5,700 equals, and when we do the math on that, we are going to say 28,000 divided by 5,700 gives us 4.9. That's about 5 half-lives. After 5 half-lives, we should have 1 half-life is 1 half left, 2 half-lives is 1/4 left, 3 half-lives is 1/8 left, 4 half-lives is 1/16 left. So 5 half-lives would be about 1/32. Okay. Go ahead and use that thinking for these questions here. Okay. And go ahead and answer the conclusion questions as part of the rest of your assignment for today.